Oh yeah, this is definitely the coin frequency for me.
I can't think of a snappy YouTube intro for this video, so frequency. When you first get your fiber, it's probably the most confusing setting that you have to deal with, especially if you're coming from the CO2 or diode laser world where you don't have to think about this setting at all. So in this video, we're going to talk a little bit about what frequency is, what it does. We'll do a little demo project, and hopefully at the end, you know a little bit more about it. All right, let's get started by first defining what frequency is, how it applies to the laser projects we're working on. I'll try to give some real down-to-earth practical analogies because I understand this can be a little bit confusing, especially if it's the first time you've heard of this concept. I'll also talk about how I personally think of frequency whenever I'm trying to figure out settings when I'm setting up my jobs. And then after we lay that foundation, we will move on into a project where I'm going to engrave 3 different coins. And the only thing I'm going to change is the frequency setting. And that way we can compare and contrast what the frequency actually did to each job. Just a quick caveat here that frequency is only one part of the equation. So you have to factor in everything when trying to decide what is the best setting for whatever you're working on. So your power, your speed, your pulse width, the frequency, and then other things like your material, the laser you have, the lens, the DPI, all of these things affect your results. But it is important to understand what each one of these things actually does. And please bear with me here. My 6-month-old decided that the family should get up at 4:30 this morning. So I'm going to try to hold this together as best as I possibly can. Okay, so starting with the definition. Frequency is defined as the number of pulses your fiber laser is firing every second. And you can see how I underlined every second there. This duration of time is going to be really important, and I'm going to come back to it over and over and over again during this presentation. So just understand that everything that we're talking about today is happening in the time frame of 1 second. And the unit of measurement we use in the laser world when we're talking about frequency is going to be kilohertz, and it'll be abbreviated KHZ. So if you go in LightBurn and you go up to the frequency box over on the right-hand side, you'll see that has the little KHZ there. It probably has it in EasyCAD as well. I don't know. I don't use EasyCAD. But just know that whenever we're talking about frequency in terms of the laser world, we measure things in kilohertz. Quick example, if you were to put 50 into that frequency input box, you're requesting 50 kilohertz, which means you are telling your laser that you want 50,000 pulses per second. If you were to put 100 in there, you're requesting 100 kilohertz. That means you're asking your laser to pulse 100,000 pulses per second. So when you're thinking of your frequency value to pulses equation, basically take the number that you're putting in that box, tack on 3 zeros to the end of it, and that is the amount of pulses that you're requesting of your laser. And we might have to rewind a bit here. So if you're unfamiliar with how your fiber laser works, it works on a pulsed-based system. So for example, if you've ever watched an old-timey movie from like the early 1900s or something, and there's a photographer with one of those big camera rigs taking a picture of someone, and they push the button and you hear that charge up, and then you see the flash, poof. Well, it's kind of the same way. This is kind of operating the same way. So what's happening is your laser is charging up and then releasing. It's charging up and then it's releasing. It's charging up and then it's releasing in a pulsed-based system. I know when we think of lasers, especially if we're watching movies and playing video games, you think of just like this solid continuous beam because that's what it looks like to us. But I think using this visualization I have here on the screen will help wrap your mind around it a little bit better. So think of your laser more like this dashed line here, where it's shooting out individual pulses. And our frequency is going to be the amount of pulses that we're shooting down to our material that we want to engrave in the time frame of 1 second. Sorry about my mouse writing here. I'm a lefty trying to write with my mouse in my right hand here. All right, 1 second. Now, how do we know what frequency numbers we can put inside of those input boxes? Because, well, there's a lot of numbers out there, right? This is really going to break down to whether you have a non-MOPA or a Q-switched laser versus having a MOPA laser. Let's start over on the left-hand side with the non-MOPA. If you have a non-MOPA, you are going to have access to a much narrower band of frequency values. So for example, you might see on your laser that you have a minimum of 20 kilohertz and a maximum of 80. Yours might say you have a minimum of 50 and it goes up to 100, or you might have one that goes from 20 to 100. It really depends on the model and the laser source and the wattage of your laser. It really depends. So it could be any combination of these numbers here, but just know that you are going to have a pretty narrow band of frequency values that you're going to have access to. You cannot use any frequency value lower than 20 or higher than 100, for example. Now, contrast that. If you have a MOPA, you have a much, much wider range of frequency values that you have access to, all the way down from 1 kilohertz up to 1,000, 4,000, sometimes even higher than that. And that's why, on average, when you're shopping for your laser and you might be comparing and contrasting models, it's the same model, it's the same brand, it's the same wattage. The MOPA version is always going to be more expensive. This is one reason why the MOPA is always going to be more expensive. So when we're figuring out what numbers we have access to that we can put into that box, you really have to figure out first what type of laser you have, what the range that you have available to you, and then from there we can start to test out different frequency values. Now let's go over some of the top line characteristics comparing a low frequency value to a high frequency value. And I added some numbers here just to kind of root these in reality. So for our low frequency value, I put 20 kilohertz in there. So that means that we are asking our laser to pulse 20,000 times per second. And then over on the high frequency side, I put 200 kilohertz in there, which means we're asking our laser to pulse 200,000 times per second. And in the grand scheme of things, 200 really isn't even that high of a frequency, but for our example here, we'll just run with it. So the two most important characteristics of frequency that we want to take note of are going to be the pulse power and the pulse overlap. I'm going to do a slide for each of these. So if it seems like I'm just kind of skimming over the information right here, don't worry. We're going to go a little bit more in detail in the next two slides. But just know that these are the two most important things to consider when we're comparing frequency values in the laser world. So starting with our pulse power here. Where's my little underline? Our pulse power. When we are operating at a low frequency, so for example, 20 kilohertz, each individual pulse, each of those 20,000 pulses that comes out of your laser is going to pack a lot of power. So each of those hits onto your material is going to be pretty strong overall. Comparing that to a high frequency value, say we're operating at 200 kilohertz, each one of those individual pulses, each one of those 200,000 individual pulses is going to carry less overall energy per pulse. It's going to be a lot more gentle hits, okay? Again, this seems like I'm skimming over this, but we'll talk about this in depth in a second here. The next important property of frequency when we want to go over is the pulse overlap. And in my opinion, this is the most important setting, and this is how I like to wrap my head around what frequency value I'm choosing. A lot of people focus on the pulse power, which is important, but I think the overlap is really what makes the differentiator in understanding how frequency works. So when we're operating at a low frequency, there is going to be less overlap. So there's going to be bigger gaps between each of our pulses. And when we're operating at a higher frequency, there's going to be more overlap. The pulses are going to start to blend together. And now, why is that? Well, let's take the example of, let's say we're going to the mall on just like a random weekday night, no holidays, no nothing, and like nobody goes to the mall anymore, so there's not a lot of people there shopping. We're going up an escalator from the first floor to the second floor, and since there's not that many people there, maybe there's one person 10 steps ahead of you, and there's one person 10 steps behind you, but you have a lot of space in between each person on the escalator. It's nice and comfy, right? You can put your bags down, no big deal. Now, compare that to, let's say you go to the mall on Black Friday. Everyone's holiday shopping, it's absolutely packed. And there's a giant line to get on that same exact escalator to go from the first floor to the second floor. Since there are so many more people, most likely there's going to be someone on the step directly in front of you. There might be someone on the step directly next to you. There's going to be someone on the step directly behind you, someone directly behind them, because we're trying to fit way more people on the same exact escalator as if we were when there was less people there. And because of that, there's the space between everyone is going to get much more compressed, right? You're going to be shoulder to shoulder with some guy eating a Cinnabon while riding up the escalator. And it's the same concept here. When we're operating at a low frequency, 20,000 kilohertz, or sorry, 20 kilohertz, 20,000 pulses per second, that's really not that much in your laser's mind. Like it can fire 20,000 pulses no problem in 1 second. So because of that, there's going to be more gaps between each of those 20,000 pulses. The gap is going to be larger between those pulses. And compare that to when we are operating at a high frequency, now we have to fit 200,000 pulses in that same exact 1 second time frame. 20,000 or 200,000 is way more than 20,000, right? So the laser has to fire a lot faster. And because there's only so much space in that 1 second duration, the pulses are going to start to blend together. Now, what are the effects of these two things here, these two characteristics? Well, at the low frequency, you're going to get an aggressive ablation, which means an aggressive removal of material and deeper cuts into your material. And that's because, number one, each individual pulse is going to carry a lot of energy, and there's going to be less overlap between those pulses. And what happens is that gap between each of the pulses gives time for your material to cool down a little bit. So, when your material cools down a little bit, you get much more effective removal. So the next pulse comes in, blasts that material, it cools down. Next pulse comes in, blasts the material, and so on and so forth. Compare that to our high frequency. Each individual pulse is going to carry less energy overall, but there's just going to be so many more of them. There's so many more pulses happening in quick succession. They start to overlap more. And what happens is you start to accumulate heat. You'll get melting effects, and you'll get smoothing and polishing effects. And that's because the laser overall is going to spend more time in contact with the surface of your material, right? Because the laser is just hitting so much faster, so many more times, that the heat is going to start to accumulate on the surface. And what happens when heat starts to accumulate on a surface? If you hold a lighter up to a piece of plastic or a candle or something, right? The wax starts to melt, the plastic starts to melt because that heat is spreading on the surface of that material. So our best use for our low frequency numbers are going to be deep engraving and aggressively removing material. And the best use of our higher frequencies are going to be fine marking, color marking, annealing, and polishing. I think color marking is a great example here. If you've ever done any color marking on stainless steel, if you were to close your eyes and rub your finger over top of that color marking on the steel, it feels like there's nothing there at all, right? That's because we didn't disturb the surface at all. We didn't do any engraving. We didn't remove any material. all we did was heat up the surface using our laser, which causes a chemical reaction which reflects the light into those different colors, you see? And normally when we do that, we operate at a higher frequency to get that effect. Okay, so now let's break down pulse power and pulse overlap separately. I think pulse power is a little bit more confusing, so we'll start with this one. For our job, we're going to assume that we have a 50-watt fiber laser. And our job, we are going to set our power to 100% and our frequency to 50. So we're telling the laser, hey, buddy, we need everything you got. We're going real hard on this engraving here. So let's break this down to the individual pulse level. I'm saying, hey, laser, I need 100% of your 50 watts of power for this job. And what is 100% of 50? 50. So we're asking for all 50 watts of power. Your laser is going to be like, all right, I'll give that to you, but I'm going to give that to you on average over the duration of 1 second, right? So it's going to make 50 watts on average available to you over the duration of 1 second. Now, we're asking our laser for a 50 kilohertz frequency. It's a reasonably low frequency, which means we are going to ask for 50,000 pulses per second. Now, where a lot of people get this wrong, I think, is they think that you're going to be getting the equivalent of 50 watts of power for each of these 50,000 pulses. And that's not how this works. Let's pretend that what I'm drawing over here, this is a scale. This is a 1 second scale. So from here to here is 1 second. And we asked our laser to provide us, oh my God, this thing is not drawing very well. I'm so sorry. 50 watts of power over the duration of this 1 second. And since we're asking for a frequency of 50, we need to put 50,000 pulses happening within this 1 second duration. Obviously, I'm not going to draw 50,000 pulses, so we're just going to pretend that this is 50,000 individual pulses of our laser happening in this 1 second time frame. What happens is each one of these pulses is going to take its own little share of the 50 watts of power. So the real equation for our per pulse energy is going to be 50 watts divided by 50,000. Now, let's say that we up the frequency to 100. We're going to divide our 50 watts of power by 100,000. So double. Now, so you can see here why a low frequency number, like this one here, is going to pack more power per pulse because it's going to be a larger number compared to this one down here. Because if you divide 50 by 50,000, that's going to be a larger per pulse energy than if we were to divide that same 50 watts of power by 100,000, right? That's going to be a smaller number. Real life example, if you and your best friend order a big pizza and the pizza gets there, and because there's only two of you, you're both going to get giant slices of this pizza. But let's say during the time that you ordered the pizza, your best friend invited 3 of his buddies over. Now you have more mouths to feed, right? The pizza didn't get any bigger, but you have to divide it more ways so more people can eat. It's the same concept here. The less amount of times you divide the total power, the more powerful each individual pulse is going to be. All right, now let's talk about the pulse overlap. So here is just a rough diagram of what this would look like. And for example, here is our 1 second duration. from edge to edge. On the top, we have our low frequency, and on the bottom, we have our high frequency. So because we are fitting less pulses into this 1 second time frame, the pulses have a little bit more space to breathe, a little bit more elbow room, right? And we know that each one of these pulses is going to pack more energy because there are less of them. And also, the overlap here is going to be smaller, which is going to allow our material to cool down a little bit. So the next hard impact of the pulse can hit it and remove material. It's going to cool down a little bit because there's a nice gap in between the pulses. It's going to get blasted again with the high energy. It's going to remove the material, and so on and so forth. It's just going to dig through your material that way. Contrast that with our high frequency down here. You can see we have way more circles happening. It's almost hard to perceive where a circle starts and where one ends. Each of these pulses is going to carry less overall energy because there's so many more of them. And they're going to start to overlap a lot. You can see how much these overlap. And because of that, your material isn't going to get enough time to cool down. The heat is going to stay on that surface. And what happens is all you're going to do is keep building up more heat and building up more heat. And this is less effective at removing material, engraving away material, but it's really effective at polishing and smoothing and gently heating up the surface for things that you'd want to do, like annealing or color marking, or if you're engraving delicate materials like plastics. This is one aspect that you would use to do that. And the last thing I want to talk about, and then we'll move on into the project because I know everybody just wants to do the project, is we'll talk about this hammer analogy. So you'll see this a lot when people are explaining frequency. They'll say, hey, a low frequency is like using a big sledgehammer and hitting your material, and a higher frequency is like using a smaller finishing hammer. And I think overall, this is a good analogy, but it's a little bit incomplete. So let's fill it in with the rest of the information that we just learned. Here is our pulses. Why is this blurry? Anyway, again, less pulses overall. Each pulse carries more energy, so each one is going to be one of these big sledgehammers. And just as importantly, there's going to be a nice gap in between each of these sledgehammer hits, which is going to let us really crank down on that material. And compare that with what would be our high frequency example, a smaller finishing hammer, because each one of these strikes is going to be less powerful individually, but because of all of this overlap, it's going to be in contact with your material a lot more frequently. So our big sledgehammer is going to be like this: boom, 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 boom. And our little high frequency finishing hammer is going to be like this: boop, 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 boop. And that is how you would fill in the blanks when people use the hammer analogy. All right. So I hope that helps clarify a little bit for how frequency works in theory. So now let's move over into our project and see how it works in real life. All right, popping over into LightBurn. This is the graphic we're going to use for our 3 example coins. It's just a random AI generated depth map design I came up with. Not my best work, but it'll work for our purposes here today. So let's open up our layer properties and input the information that we want to go with. So I have a 60-watt JPT MOPA fiber laser. So that means if we go back to our frequency range talk, that I have access to that really, really wide range of frequency values from 1 all the way to, in my case, 4,000 kilohertz per second. But I'm not going to do anything crazy like that. So let's start by filling in our speed. So the speed I'm going to use is 2000. And the power I'm going to set this at is 80. So this is a little bit less than what I normally would use. I usually go 85 to 95 range whenever I'm doing my coins, but I think this is going to help me prove a point with this frequency example. And if it doesn't, I'm just going to look like an idiot. But I think I'm doing this for a reason, and I'll explain it in a little bit. So my max power is going to be 80%. Frequency, here we go. I'm going to set for my first coin, I'm going to use a low frequency. So I'm going to set it to 48 kilohertz. And you might be thinking, well, that's a really weird and random number. Why would you choose 48 as your low number instead of something like 20, like we talked about earlier in the presentation? And that's because of something called a cutoff frequency. So I don't want to blast your brains with any more information, but my laser and most MOPAs have what's called a cutoff frequency, which is your manufacturer saying, hey, any number that you choose below or above this cutoff frequency, I'll let you put that information into the system here, and I'll let you run it at that number, but I can't guarantee that I can keep the pulsing cycle. I can't guarantee that I can keep the pulsing cycle stable, especially if you put a number that's too low in there. So if I were to put 20 in there, my laser is going to be like, hey, you're asking me to generate and store a lot of pulse energy. And I don't think that I can stably do that without potentially damaging the insides of your laser parts. So what the controller does, it's kind of like the safety monitor, the hall monitor of your laser, it starts to scale your power down. And there's a whole chart you can find depending on your manufacturer that tells you exactly how much you're going to scale your power down. So since I want 100% of my 80% power, I want to use all the power just as it's written here. I know that my lowest frequency that I can use to make sure everything stays stable is 48 kilohertz. So that's what I use when I want my bare minimum low frequency value. And if you have a MOPA, you'll have a box here for Q pulse width. Mine defaults to 200, so I'm leaving it at 200. If you have a non-MOPA, you're not even going to have this box here. Yours is just pegged at whatever it is. It's usually like 100. Doesn't matter, though, for this example. For my file, I am running it at 900 dpi because I designed this file to be 900 dpi. 45-degree scan angle, doesn't really matter. Image mode, 3D slice, that's going to give us that 3D look to our coin. Enabling the cleanup pass, I'll talk about that in a second. The angle increment, this stuff doesn't matter. This is just random stuff that I put in here because I like to. And the number of passes I'm going to run is 256. For my cleanup pass, I'm going to run it pretty fast. So 3,200 millimeters per second speed, a max power of 25%. So that's a pretty low power. And then a frequency of 100. So I debated not running a cleanup pass because it's going to interfere a little bit with the point I'm trying to make with frequencies, but it's going to run so infrequently that I don't think it's actually going to matter too much at the end result. So just know that I am setting my frequency a little bit higher for my cleanup pass to 100, and I'm running it after every 8 passes, okay? So let's run this, and then we will come back and switch it to the next stage. First coin down, so let's update our frequency for the second coin. So I'm going to open up my layers panel here, and everything else I'm going to leave exactly the same. However, I am going to change my frequency to a value of 80. So 80, again, so 80,000 times per second is going to be a higher frequency than 48,000 times per second. So ideally, it's going to look a little bit smoother in my end result. I hope, at least. I usually run my coins around the 80 range because I'm looking for a nice middle ground between really, really aggressive removal and slightly smoother results. So 80, 85 is usually where I run my my coins around. And if you have a non-MOPA, this would be like the top range. This might be the top range of your frequency. So you might not be able to go any higher than this one here. So let's set it to 80, click OK, run this job, and then we'll come back. Second coin down. Now let's set the frequency for our third and final example. And for this one, I'm going to do something I've never done before. So I've run coins at 48 kilohertz in that range. I've run coins in the 80 kilohertz range. I have never run a coin at anything higher than 100. So I'm going to run my frequency at 200 kilohertz. So that's 200,000 pulses per second. I'm not exactly sure what's going to happen here, but at least it should be interesting to look at. I think the only thing I want to change here is, since my cleanup pass is now less of a lower frequency than my engraving pass, I'm going to update that a little bit. So let's change the cleanup pass to something higher. Normally, you always want to have a higher frequency value for your cleanup pass versus your engraving pass. So I'm going to set this to, let's go with 300. Again, I have a MOPA. I can do things like this. I can really stretch out my frequency band, and that's one benefit of having one. So my engraving pass is going to be, again, all the other values are the same, except my frequency is 200 now. And my cleanup pass, the same, except my frequency is going to be 300 kilohertz. Let's run this, see what happens. Now let's compare our test results. So as far as cleanup goes, I didn't do a whole lot. All I did was hit it with some steel wool, some fine steel wool with some water and some dish soap just to kind of clean it up and shine everything up a little bit. But I only spent a couple minutes on each coin. So it's a fair comparison across the board here. Starting on the left side, this is the 48 kilohertz example. This is the 80 kilohertz example. And this is the 200 kilohertz example. So starting with the lower frequency. If we look at our image here, the thing that stands out the most is just how rough and noisy the background is. Look at that. It looks like I textured it on purpose, but I didn't. That's just what happens when you run a lower frequency with a more powerful pulse, with more gap time in between the pulses. It's just going to impact and crater your image much more and leaves it with an overall noisier look. All right. Moving on to the 80 kilohertz example. And we can see that the background's still a little bit noisy. It's a lot smoother than the other one. So comparing the two backgrounds here, it's definitely a lot smoother, but it's still there. It still looks like it has like a little textured effect to it. And even across the front face here, you can still see some of it, but overall, not bad. Now, for the 200 kilohertz example, this is the one I was most interested to see because I've never done this before. And look at that background. Look how smooth that is. It's almost like a perfect smooth dish look. And that's because the higher frequency, the laser spent more time in contact with our brass, therefore it smoothed it out. And even as far as going across the face, I got a lot more depth than I was expecting. I thought that since the frequency was so high and the power was pretty low, that it wouldn't really engrave much, but there really isn't that much of a difference in depth going from the 48 kilohertz up to the 200 kilohertz, which kind of surprised me. I thought that I would get a lot more on this one versus this one, but it just goes to show that tweaking your frequency isn't going to bring gigantic changes to the depth that you're going for. You'd have to change your speed and your power to get more noticeable results. But yeah, like this is a really, really interesting comparison. And it's definitely got me thinking. I might start running at a slightly higher frequency than I normally do if I can still get results that look like this out of the box. And that's just what I did. My curiosity got the best of me, so I grabbed another blank coin and I went back in the LightBurn. I changed two things. I bumped the power from 80% up to 90%, which is closer to the range that I normally use. And then I changed the frequency to 100. Let's see what happens. And here's a finished look at that final attempt where I changed my frequency to 100 kilohertz and I applied some brass black, but this is definitely the frequency for me. The background is nice and smooth. There's nice details throughout the face. I have to fix the file a little bit just to get some of these errors out of here, but overall, this coin really looks nice. And honestly, I probably wouldn't have even tried it if it wasn't for the experiment that we ran today, where, that 200 came out looking pretty good. So I figured I could probably bump this up a little bit into the 100 range. And I think that's where I'm going to stay. So I hope today's explainer was helpful to you. If you have any questions, you can pop them down in the comments section below. Otherwise, I'll catch you next time.